Good afternoon, everyone. Thank you for coming. My name is Tiffany Kataria. I'm from the Jet Propulsion Laboratory.
And my name is Kevin Stevenson. I'm from the Space Telescope Science Institute.
And today we'll be talking to you about the search for life with the Origin Space Telescope. All right, so to start, here's a picture of Earth. In thinking about Earth and other planets, we want to talk about exoplanets. Exoplanets are planets that orbit other stars away from Earth, as seen from Earth. We've discovered over 3,000 exoplanets so far. It is in fact a booming field. And we've discovered planets ranging in size from Jupiter to Mercury. Kepler has shown us, in fact, that small planets are common in our galaxy, but most characterization efforts to date, in terms of understanding what these planets are made of, have been prioritized for larger planets simply because that's easier to do. But ultimately, we really want to know, are we alone? We want to seek out an Earth twin, and so let's do that in this movie. So here's Earth. We're moving away towards our distant galaxy, a nearby M-dwarf star. And M-dwarfs are particularly interesting targets in our search for life because their habitable zones, that is, the regions that are expected to house liquid water, are much closer to their stars, and therefore we expect that we can see these planets transit those stars. And so here we are traveling to a nearby M-dwarf and zooming in to that particular potentially habitable planet. This is one of the TRAPPIST-1 planets in our system. And what's unique about M-dwarf planets is that because they're so close in, we expect them to be what's called tidally locked or synchronously rotating. So they have these permanent day sides and permanent night sides. And so these regions of habitability could extend from these permanent night sides to these colder night sides or not. They're really interesting laboratories for understanding not only the potential for life, but these atmospheric processes, the weather and chemistry that takes place on these dynamic worlds. So why M-dwarfs? Why are we looking at M-dwarfs particularly in our search for life? Well, for one, they're the most common star in our galaxy. 75% of the stars in our galaxy are M-dwarfs. And this simulation is showing the RECON survey, which surveys the nearest stars within 15 parsecs, or 25 parsecs, from us. And so what this simulation is looping through different sorts of objects. And what it's ultimately showing you is the vast number of M-dwarfs that are within this 25 parsec difference. And so there's a big potential for searching quite a large sample of stars to search for planets in their habitable zones. Not only are the stars themselves common, but the likelihood that there is a small planet orbiting a star within its habitable zone is also high. So as these plots on the right are showing you occurrence rates from different simulations for tests and other surveys, Kevin will talk about in a little while. But ultimately, we expect that at least 25% of these M-dwarf stars will have planets in their habitable zones. And so they're really interesting and compelling targets in our search for life. Also, because this is a relative measurement, we're measuring these transits as the planet passes in front of its star. The transit depth is larger because the star is smaller and cooler, and therefore it's easier to characterize. All right, so just to review, what is the transit technique? The transit technique measures the dimming of starlight as a planet passes in front of the star as seen from Earth. And so this animation here is showing the TRAPPIST-1 system, which some of you may be familiar with. This is a 7-planet system of roughly Earth-sized planets orbiting an M-dwarf star. And so as you'll see in this animation, it's illustrating the transit technique. So as the planet is passing in front of its star, you're seeing this dip in brightness as a function of time. And this is proportional to the planet's size. So a smaller planet will block out less light, a larger planet will block out more. And so therefore you have a measurement of the planet's size. But you can also use complementary techniques such as the radial velocity technique, which measures the gravitational tug between its planet and its star. You can use something called transit timing variations, which has been used actually within the Kepler survey to measure interactions between planets and multi-planet systems to ultimately constrain the planet mass. And when you have mass and radius, you can constrain a bulk density of a planet. And so you can determine whether or not this planet is rocky, like Earth, or gaseous like Jupiter or an ice giant. And so if we have that information, we have a comprehensive picture of whether or not this planet is rocky, and then we can search for biosignatures to determine if this planet is in fact habitable.
Okay, So moving on, there are numerous ground and space-based missions currently looking for transiting exoplanets. Tiffany just pointed out to you the TRAPPIST system, which has 7 planets discovered within that, 3 of which are in the habitable zone. In addition to the TRAPPIST mission, there's also, for example, the MIRF project, which recently discovered LHS 1140b. This planet is a super-Earth orbiting around a mid-M dwarf, and it too is in the habitable zone of roughly 250 Kelvin. There are future missions coming online. For example, Speculos is a European mission which will be looking for transiting planets around mid to late and even ultra-cool M dwarfs. These are even moving towards the brown dwarfs. And this will be looking both in the northern and southern hemispheres. Now, many of you may be familiar with the Kepler mission. K2 itself is looking for transiting exoplanets from space. It is currently operational. It's been doing that mission for the last few years. But soon, coming up, we'll have the Transiting Exoplanet Survey Satellite, also known as TESS. It's going to be launching in March of 2018. And here we'll be doing an all-sky survey of the closest, brightest host stars looking for transiting exoplanets. And they do expect to find numerous planets around M dwarfs. In addition, we have Plato, which is in the bottom right-hand corner down here. This is an ESA mission that is currently scheduled to launch in the mid-2020s. They too will also be looking for MG, K, and M dwarf stars hosting transiting exoplanets. All told, we can expect to have dozens, even hundreds of planets detected orbiting around M dwarfs. So, just because we find a planet in the habitable zone, that doesn't mean it is inhabited. There are very important distinct features that we need to measure before we can claim that we've detected life. So the discovery of a potentially habitable planet requires the detection of biosignatures. Now, biosignatures are essentially produced by living organisms, and they leave the atmosphere out of equilibrium. Now, a simple example of what a biosignature is methane and ozone. The two measured in an atmosphere can only be created by life. And so if you detect both ozone and methane, you'll know that it is most likely to be determined by life. Now, there are 2 other molecules in the mid-infrared that are important for measuring biosignatures or inferring the presence of life. That are water and CO2, carbon dioxide. They are what we call bioindicators because they are necessary for life, but their detection doesn't necessarily mean that we have life. So we would really want to detect all 4 of these molecules in the mid-infrared before we can determine the presence of life. So how are we going to do that? How are we going to make this measurement? Here we have a depiction of the Origins Space Telescope, OST. OST is one of the 4 mission concepts currently under review for the 2020 Decadal Survey. It is oftenly referred to as, or jokingly referred to as, the Big Cool Telescope. Big because it's 9.1 meters in the primary aperture, and cool because it's cooled down to 4 Kelvin. Now, this represents a significant improvement in terms of the sensitivity level from previous missions, including Spitzer, Herschel, and Sophia. In fact, it's more of 4 orders of magnitude improvement in sensitivity. We'll be building a dedicated instrument for transit spectroscopy, and it will use interesting new technology like a densified pupil spectrograph and innovative new detectors that allow us to reach the necessary precisions to detect biosignatures. The goal for OST is to have a precision of 5 ppm or less in order to make a definitive measurement of biosignatures. Misc will operate in the mid-infrared from 5 to 25 microns, and will have a resolution of about 100 to 300. So here's an example simulated spectrum that we might get with the Misc instrument from OST. So what I'm showing you is a thermal emission from a habitable zone planet. In this case, I picked TRAPPIST-1e. And what you can see is that we have in blue JWST's MIRI LRS spectrum from 5 to 12 microns, and in red, the OST spectrum from 5 to 25 microns. Now here we've assumed 30 secondary eclipses. This is where the planet crosses in behind the star to make this measurement. And you can see that we can measure the thermal emission. This indicates right here, the black body curve is thermal emission coming from the planet itself. So we can claim that we've detected photons from a habitable zone planet with just a few secondary eclipse measurements. From there, we can continue on to achieve higher and higher precision, looking for example, CO2 and water, and in order to make a definitive measurement as to whether or not the planet has an atmosphere. In addition to this secondary eclipse measurement, we can also obtain data from the primary transit. This is when the planet crosses in front of the star. and we measure light as it passes through the limb of the star itself, going through the atmosphere. And so in this case, when we have an absorption feature, it more looks like a bump. So the CO2 feature goes upwards instead of down, as in the previous figure. And so we can measure with, again, 30 transits, we can detect carbon dioxide at high signal to noise, ozone, and also methane. And so again, if we have that detection of both ozone and methane, then we can definitively claim that we have indications of life in that planet. Now, there's a third measurement that I didn't talk about, and that is the phase curve measurement. This is where we can measure or observe the planet as it makes one complete rotation around the star. And so what happens is that we can obtain light or emission from the planet as a function of longitude, because as Tiffany mentioned, these planets are tidally locked. And so as the day side comes into view in this graphic, you can see the temperature increases and we increase the measured relative flux. And as the night side comes into view, the temperature drops back down again and we don't receive that flux. So we really obtain constraints on the climates of these atmospheres, and we can determine whether or not these planets have substantial atmospheres, which are, of course, very important for life.
All right, so in summary, M dwarfs are important targets in the search for life. They're very common stars, and we expect actually that, in fact, habitable zone planets around those stars will also be very common. OST will target these terrestrial exoplanets in the habitable zone of M dwarfs to detect biosignatures and also constrain habitability via these thermal measurements. OST will also enable technical advances with detector technology and densified people spectrometer. And ultimately, OST will be able to leverage the heritage of characterizing transiting extrasolar planets with Spitzer, with Hubble, and with JWST in extending high-fidelity measurements of transiting exoplanets to the mid-infrared. Thanks, and we'll take questions. I should also mention, if you're taking part in the OST scavenger hunt, the secret word is OST plus exoplanets. Thanks.
Transiting planets, they don't always transit at the same time necessarily, but they do transit very close to one another. And in fact, that's actually a benefit, because if you stare at the star for, say, 10 or 15 hours, you could get 2, 3, 4, sometimes 5 transits at a time, and that'll allow you to characterize the atmosphere of all 5 of these planets within a short period of time. Now, if 2 of these planets are transiting at the same time, you can actually differentiate their signals. It becomes additive. So you can, and if you're really lucky, you could actually have one planet transit across another planet itself, which becomes a really unique and interesting type of observation that we would really love to have. Yep.
So you said that if you have ozone and methane together, that's unambiguously a biosignature. Are there any other unambiguous biosignatures?
Yeah, there are other molecules. Ozone, so the question is are there any other molecules that are unambiguous in terms of a biosignature detection? Yes, so ozone is one example of an oxygen-based molecule. O2, the molecular oxygen, is also what we consider part of the biosignature family. In addition, nitrous oxide. So oxygen, O2, we aren't sensitive to in the mid-infrared, but you could do that using ground-based observations at about 770 nanometers, which would complement the mid-infrared space-based observations. Nitrous oxide is available from the mid-infrared, and there are multiple molecular features. All of those do require the combination of some oxygen-based molecule and a hydrogen, such as, a carbon-based, such as methane.